Hi, I'm Yoon at Seoul National University, and I'm going to present mmTLS, which is a framework for scaling the performance of encrypted network traffic inspection. TLS is a popular network protocol that supports end-to-end authentication, confidentiality, and content integrity. For recent trend, over 80% of websites use TLS, and most of them use the latest version, 1.3. In terms of encryption scheme, AES GCM is the most popular one. TLS ensures the outside attackers cannot sniff nor modify the traffic. But what if the attackers use the TLS channel for attack? Then malicious content will easily infiltrate into your computer by clicking a binary in an email. So we need a TLS middlebox to monitor the encrypted traffic. There are two main goals of a TLS middlebox. The first goal is network security monitoring. One can unintentionally download a virus or malware from a compromised server. The TLS middlebox detects or prevents such incident by monitoring the downlink traffic. Existing IDS or IP systems such as Snort, Srikata, and Zig already play this role. The second goal is data loss prevention. One can leak the confidential data of an enterprise, but a modern TLS middlebox can detect such content and prevent leakage of the confidential data. So security-sensitive parties such as government, enterprise, or school mandatorily employ the TLS middleboxes. Then how do the existing TLS middleboxes operate? To decrypt the content and inspect the plain text of the traffic, typical TLS middleboxes split the TLS connections into two connections. That is, there is one TLS connection for the client side and the other one for the server side. However, the split connection middlebox incurs two critical problems. The first one is performance issue. The split connection middlebox should relay two TLS connections. And this means that it should do everything twice, such as TLS TCP handshake, tear down, flow control, or congestion control, which have been already done between the two endpoints. Also, because it uses different session keys for each connection, it must re-encrypt the plain text after decryption. What is worse is that even though it does not want to monitor the whole content, every TLS record should be re-encrypted after decryption. So we run a simple benchmark test to understand the performance degradation incurred by the split connection. When we use our machine as a TLS endpoint server, the throughput is 143 Gbps per second. However, when we use the same machine as a split connection middlebox, the throughput plummets to 39 Gbps per second. So the performance decreases by about 73%. Note that it is a fundamental issue incurred by the split connection because not only the split TLS middlebox, but also a simple TCP proxy suffers from the architectural bottleneck due to the split connection. The split connection incurs a critical security issue as well. The TLS protocol should authenticate the endpoint server using the server's legitimate certificate. However, in the split connection, the middlebox impersonates as the real server using a forged certificate. Moreover, in order to make the clients trust the forged certificate, all the clients should install a fake root CA certificate on themselves. Thus, the client can never do end-to-end authentication with the real server in the split connection scheme. Also, in the split connection, the middlebox has all authorities over the whole content. It can do not only inspect the content, but also modify the content and generate the legitimate record tag for the modified content. It means that the both endpoints can never detect whether the content is modified or not. What if the middlebox is compromised? All the clients connected to the middlebox will be easily exposed to the malicious attackers. To enhance the security of the split connection, many recent works make the middlebox participate in the end-to-end TLS handshake and they try to make the middleboxes trustworthy. However, since the endpoints should negotiate session keys with each middlebox, they suffer from the additional overhead. And also, there should be intrusive modification in the existing TLS handshake procedure. Moreover, because the previous works assume that the middleboxes are trustworthy, the endpoints cannot detect illegal content modification by the compromised middlebox. On the other side, some recent works suggest search-over encryption for network security monitoring. Search-over encryption is a technique that allows pattern matching on ciphertext rather than on plain text. When using search-over encryption, the middlebox does not need to decrypt the ciphertext, so there's no security issue like the man in the middle. However, such an approach mandates specific crypto algorithms, which make them hard to deploy. Unlike the previous works that try to improve the TLS protocol over the split connection middleboxes, we focus on the underlying connection. First of all, why do we need to split the connection? Previous works used split connection to allow trustworthy content modification on the middleboxes. So we analyzed various types of client-side middleboxes. As shown in the table, some of them need to modify the content indeed. However, what we found is that the transparent web cache and web optimizers have largely disappeared today thanks to the significant improvement in network bandwidth and its cost. Also, the functionality of the ad tracker blocker has already moved to the third-party application of the clients, since the middleboxes cannot catch up with the fine-grained blocking policy. Thus, in a typical enterprise environment where only read-only middleboxes are deployed, we do not need to allow trustworthy content modification on the middleboxes. And it means that we can make a TLS middlebox which does not split the connection. Instead, we make the clients explicitly share the session keys to the middlebox. And by doing so, we can significantly improve the performance of the middlebox. And we can achieve good security since non-split connections naturally ensure the end-to-end authentication. Also, because the single connection middlebox is seamless, it is much easier to deploy it in real world. Our work, mmTLS, operates on a single connection with out-of-band session key sharing. First of all, the client establishes an out-of-band TLS session to the middlebox for secure key sharing. Then, upon establishing an end-to-end TLS session to the server, the client sends the end-to-end session keys to the middlebox via out-of-channel. After that, the endpoints can send and receive the application data as if there is no middlebox. Meanwhile, they communicate with each other. The middlebox transparently reassembles the TCP flows and can detect and monitor them. Note that there is no re-encryption since the middlebox forwards the packets without any modification. Let's focus on what the middlebox does. In the middle of the end-to-end TLS session, it passively monitors the TCP states of endpoints and reassembles the TCP packets to TLS records. If a new record is ready to be read and has application data, the middlebox application can decrypt and monitor the record. Unlike the previous works, the mmTLS does not participate in the end-to-end TLS handshake. If the reassembled record is related to the TLS handshake, it skips decryption of the record, and so there is no overhead on the middlebox during the TLS handshake. By doing so, mmTLS can increase the performance of the middleboxes. And in terms of security, mmTLS naturally supports end-to-end authentication. But what about end-to-end content integrity? Using the decryption key, the middlebox can do not only decryption, but also encryption and text generation. So when the middlebox receives a record, it can modify the content and generate a new tag for the modified content. Then the receiver will verify the tag by generating the tag from the modified content, and it will think that the record is legal. If you can trust the middlebox, there seems to be no problem. However, what if the middlebox middlebox is compromised. Then the endpoints will never notice that there was an illegal content modification. Our solution is using a separate end-to-end key to generate a private tag that the middlebox cannot generate. Now the sender appends the private tag to the original record. Then the middlebox receives the record with the private tag. The middlebox still can modify the content and generate the tag from the modified content, but it cannot generate the private tag because it does not have the key for the private tag generation. Then the receiver will verify the private tag by generating it from the modified content and detects that the private tag is wrong. However, the private tag generation incurs additional overhead at endpoints. About 20% of the CPU cycles are used for generating the tags when sending a large object. So naively adding one more tag generation means that the throughput of server will be decreased by 20%. To minimize the overhead, we analyzed the original tag generation procedure and found that, first, the tag generation load is linear to the data size. Second, the integrity of the content is already guaranteed by the original record tag. From those insights, we designed a new technique for private tag generation. We generate the private tag from only the original tag, excluding the content. Because the size of tag is only 16 bytes, the overhead for private tag generation becomes negligible. In terms of performance, there was another challenge in our design. When using multi-cores on the middlebox, we use receive size scaling, in short RSS, for scalable packet processing. For your information, RSS hashes the 4 tuple of each packet to determine the CPU core and ensures that packets in the same flow are read and processed by the same core without a lock. Using RSS, mmTLS can consistently forward the packets to the responsive core. However, mmTLS middlebox should process not only the data packets, but also the session keys received via the out-of-band channel. Since the out-of-band channel has different 4 tuple from the data packets, RSS will end up forwarding the key packet to another core. So we need additional inter-core key delivery, but it degrades the performance and scalability. As a solution, we exploit a SmartNIC as a session key forwarder. A normal TLS server is running on the SmartNIC, and it is now responsible for all out-of-band channels for the security sharing. To make the SmartNIC able to steer the keys, the client delivers not only the keys, but also 4 tuple of the TLS connection that's being monitored. Then the SmartNIC forwards the key packet to the host with a custom UDP header filled with the 4 tuple of end-to-end TLS session. By doing so, now the 4 tuple of key packet is the same with the 4 tuple of the data packet. And finally, the RSS will steer the keys to the responsive core. Using this technique, mmTLS scalably utilizes multi-cores without any additional overhead. For easy development of the TLS middlebox, mmTLS supports event-driven TLS traffic monitoring, which helps the developers focus on the main logic without background knowledge of the TLS or TCP protocol. mmTLS supports many useful events during the TLS session. For simple examples, there are on-TLS handshake start event and on-TLS handshake end event. To develop a monitoring middlebox, the key event is on-TLS new record event. It means that the new TLS record is reassembled and it is ready to be read by the application. The developer only needs to register a callback function to write the action on this event. In addition, mmTLS supports on-demand decryption. If the application no longer needs to see the plain text for some sessions, it can stop decrypting and monitoring at any time. And since mmTLS is always tracking the TLS sequence number, the application can also resume the decrypting and monitoring at any time. For a simple example, using the on-demand decryption, application can decrypt and monitor only the first 10 kilobytes of the HTTP response. We implement mmTLS by extending MOS, which is a middlebox OS, supports TCP state monitoring. mmTLS currently supports every cipher suite of TLS 1.3 and even an old one like AES CBC. Session key forwarder on the SmartNIC is implemented as a Linux EPOL-based OpenSSL server. For the mmTLS clients, we built a common library for key sharing, and by linking it, any clients can be easily ported to support mmTLS. We implemented private text generation using optimized G-hash instructions supported by the Intel CPU, and finally built an mmTLS ported nginx server. This is our evaluation setup. We use 4 clients and 2 backend servers. For clients applications, we use htload, AB, and Chromium web browser with mmTLS support. For server application, we use nginx TLS server. And for the middlebox under test, we built a sample application on mmTLS, which decrypts the first 64 kilobytes of HTTP response. And for the first baseline, split TLS, we use nginx TLS proxy. And for the second baseline, we use mmTLS as secure split TLS middlebox. For cipher suite, we mainly use AES GCM on TLS 1.3, which is the most popular cipher suite today. And for comparison with an existing work, mmTLS, we added support for AES CBC on TLS 1.2. We evaluate the throughput of persistent connections using 4,000 concurrent connections for 2 cipher suites. For the first cipher suite, which is the most popular one today, mmTLS shows up to 4.6 times better throughput than the split TLS middlebox. And for the second cipher suite, which is used to compare with mmTLS, mmTLS shows up to 9.6 times better throughput than split TLS or mmTLS. Then we evaluate the throughput of ephemeral connections, which requires TLS handshake for each request. mmTLS shows more than 41.2 times higher throughput than the split TLS, and 58.8 times higher throughput than mmTLS. This significant improvement is mainly because mmTLS does not participate in the TLS handshake, while the split TLS should do the TLS handshake twice. In general, ephemeral connection spans about 90% of CPU cycles for TLS handshake, so the result is reasonable. We measured the page load time to the popular websites using mmTLS ported Chromium web browser. For your information, the baseline end-to-end TLS means when there is no middlebox between the endpoints. And as a result, mmTLS shows the same page load time with the end-to-end TLS as if there is no middlebox. What if the middlebox does DPI after decryption? We added DPI function using hyperscan and 10K snort rule set to both mmTLS and split TLS, exactly the nginx TLS proxy, and increased the amount of content for DPI gradually. Since DPI for 10K snort rule set spans a lot of CPU cycles, of course the overall throughput decreases when the amount of DPI increases. However, mmTLS DPI still shows 2.7 times better throughput than the split TLS DPI. In summary, we showed that the root cause of security issue is splitting, and the performance bottleneck of split TLS middlebox is in relaying 2 TLS connections. mmTLS removes redundant and unnecessary operations incurred by the split connection. And mmTLS adapts scalable key distribution technique. And also, mmTLS benefits from an efficient private text generation technique to prevent illegal modification by the middleboxes. In addition, unlike the previous works, mmTLS provides event-driven API and on-demand decryption for easy and efficient development. With such techniques, mmTLS outperforms the baselines without any security degradation. So if you want to develop your own TLS middlebox, please use our mmTLS. Thank you for listening.